In today's video, we are going to explore fuel cells and take a close look at how the hydrogen-oxygen fuel cell actually works. We will also understand its structure and discuss the main advantages and disadvantages of using this technology in the real world. A fuel cell is a special type of electrochemical cell, which means that it can convert energy between electrical and chemical forms. More specifically, it transforms the chemical energy stored in a fuel and oxygen directly into useful electrical energy, which we can then use to power many different devices. There are several types of fuel cells used today, but the most common and most studied one is the hydrogen-oxygen fuel cell. This cell combines hydrogen gas with oxygen gas to produce water, and during this process it generates a large amount of electrical energy that can be harnessed immediately. Now, let's understand how this system is built. The structure of a fuel cell can seem a little complicated at first glance, so it helps to break it down step by step. At the very center of the setup is the electrolyte, which is a medium that allows ions to move freely between the two sides of the cell. Different types of electrolytes can be used, but one of the most common examples is potassium hydroxide. On each side of this electrolyte, we have two electrodes. The anode is placed on the left and it carries a negative charge, while the cathode is on the right and it carries a positive charge. These two electrodes are connected by a wire on the top, which provides a path for electrons to flow from the anode to the cathode. One detail that often confuses students is that in a fuel cell, the anode is negative and the cathode is positive, which is the opposite of what happens in electrolysis, where the cathode is negative and the anode is positive. So it is important to remember this difference carefully to avoid mixing them up. Both electrodes in a fuel cell are made of porous carbon, which means that they contain many small holes. These holes allow gases to diffuse easily, and each electrode also contains a catalyst to help speed up the chemical reactions taking place. Surrounding each electrode are compartments. The one around the anode is called the anode compartment, and the one around the cathode is called the cathode compartment. Each of these compartments has an inlet at the top. Hydrogen gas enters from the left into the anode compartment, while oxygen gas enters from the right into the cathode compartment. After the chemical reactions are complete, water and heat produced in the process exit through an outlet on the cathode side. Now that we understand the structure, let's move on to how a hydrogen-oxygen fuel cell actually works. When hydrogen gas enters the anode compartment, it meets the anode catalyst and undergoes oxidation. This means that each hydrogen atom loses an electron and becomes a hydrogen ion. The electrons that are lost travel around the outer wire toward the cathode, while the hydrogen ions pass through the electrolyte toward the same side. At the cathode, oxygen gas enters and reacts with these incoming electrons and hydrogen ions to form water as the product. For this reaction to be balanced, each molecule of oxygen needs two sets of hydrogen ions and electrons, so the overall chemical change at the cathode involves one oxygen molecule reacting with four hydrogen ions and four electrons to produce two molecules of water. Once formed, the water and any heat leave the cell through the outlet, and the entire process continues as long as fuel is supplied. The two reactions happening at the anode and cathode are known as half equations because each one shows either a loss or a gain of electrons. When we combine these half equations, we get the full balanced equation for the fuel cell, showing that hydrogen and oxygen combine to form water while releasing electrical energy. This electrical energy is produced because the electrons move through the external circuit from one electrode to the other. In a diagram, we often show this energy lighting a lamp, but in practice it can power almost any electrical device, from a small motor to a car. When explaining how a fuel cell works, it is crucial to remember that as the fuel enters, it becomes oxidized, and this oxidation process creates a potential difference between the two electrodes. The hydrogen loses electrons, and the difference in charge between the anode and cathode is what drives the flow of electrons through the circuit, allowing electricity to be generated continuously as long as fuel and oxygen are supplied. Now, let's look at the pros and cons of hydrogen-oxygen fuel cells. Although they can theoretically be used to replace large power stations, their main application today is in vehicles as an alternative to polluting fossil fuel engines and heavy chemical batteries. One of the greatest advantages of fuel cells is that they only require hydrogen and oxygen to operate, both of which are abundant resources. The only product they release is pure water vapor, which means they do not emit carbon dioxide or other harmful pollutants. Another benefit is that fuel cells are relatively simple in design and can last longer than traditional batteries. They are also easier and safer to dispose of at the end of their life compared to the toxic materials used in conventional batteries. However, there are also some drawbacks. Hydrogen gas takes up a lot of space because it is very light and less dense than liquid fuels, making it difficult and expensive to store. It is also flammable and can be explosive when mixed with air, which requires careful handling and safety systems. Finally, while hydrogen fuel itself is clean, the process of producing it usually requires energy, and in many cases that energy still comes from burning fossil fuels. So although fuel cells are environmentally friendly during operation, the overall system is not yet completely green unless the hydrogen is produced using renewable sources such as solar or wind power. In summary, hydrogen-oxygen fuel cells are a remarkable technology that can produce electricity cleanly and efficiently. They show us how chemical energy can be turned directly into electrical power without harmful emissions, but challenges in hydrogen production and storage still need to be overcome before they can replace fossil fuels on a large scale.